Hey, sports fans, welcome to Sequences to Infinity and Beyond. Let's get started. Sequences. Sequences are a group of numbers that are usually defined by some rule, and so they usually have a distinct pattern. And there's two different types of sequences, infinite sequences and finite sequences. This first example down here is an example of a finite sequence because it has a finite number of terms. Whoa, that's not the tool I wanted. A finite sequence, because it has a finite number of terms. It has 5 terms. An infinite sequence is a sequence that goes on forever. It has an infinite number of terms. A little bit of notation here. Sometimes we will list the terms in a sequence, a sub 1, a sub 2, a sub 3, and then we'll say dot 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 down to a sub n, where a sub n is the last term. And each number in a sequence is called a term. So when we say terms, we're talking about the pieces of a sequence. Okay. Excuse me, an infinite sequence, like I said, is one that goes on forever. It might be defined by, usually is defined by some sort of rule. So like in this example here, the 2, 4, 8, 16, 32, our rule is 2 to the n. In other words, we could say if you want any term in that sequence, the nth term, you want the 5th term or the 3rd term or the 100th term, we'd say take 2 to the n. So for example, if I wanted, let's kind of draw a line in here, if I wanted the 10th term, that would be 2 raised to the 10 power. Okay, so that's an example of an infinite sequence that goes on forever. That's usually indicated by this dot 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 here. Okay. Let's look at this other way of kind of defining sequences. If I put kind of this rule in brackets, so I've got 2 raised to the n plus 2 for n equals 1, 2, 3, and so on forever. Once again, this dot 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 means it goes on forever. Then that means I'm going to take 2 to the, let me kind of list the terms here. Take a sub 1 is 2 to the 1 plus 2, which would be 2 to the 3. And a sub 2, that's the second term, would be 2 to the 2 plus 2. That'd be 2 to the 4. And so on. Okay, so that's a rule for a sequence that goes on forever. 2 to the n plus 2 is the rule for all n, 1 through infinity. Alright? Let's move on here. Okay, find the first 6 terms in the sequence. So suppose we had a sequence that was defined by a sub n equals n times n plus 1. We want to find the first 6 terms. Hopefully we'll be able to find a pattern here. So we won't have to do the rule each time. But this is going to be 1, a sub 1 is going to be 1 times 1 plus 1, which is 2. A sub 2 is going to be 2 times 2 plus 1, which is 6. A sub 3 is going to be 3 times 3 plus 1, which is 12. A sub 4, you guys get the idea, is going to be 4 times 4 plus 1, which is 20. A sub 5 is going to be 5 times 5 plus 1, which is 30. And then a sub 6 is going to equal 6 times 7, which is 42. Okay, so there's the first 6 terms in this explicitly defined sequence. It's explicit because no matter, if I want to find the nth term, I can put it into the formula explicitly. I can just put in 9 here if I want the 9th term, or 15 if I want the 15th term. We're going to talk about recursively defined sequences, which so that'll help you kind of see the difference between the two. Alright, recursively defined sequences. These are sequences that depend on the previous term. Okay, so for instance, and you need 2 things for a recursively defined sequence. You need the first term, because I need to know where we're starting, and then I need the rule. Okay, so there's 2 things. There's the rule and the first term. So a sub 1, I need that, and then I need my rule. Okay, which is a sub n equals 2 to the n minus 1. This a sub n minus 1 is the previous term. So for instance, if I wanted the 4th term, I would take 2 times the 3rd term. And we'll see how that works here in a second. But a sub 1 is 2. Alright, then I want the 2nd term. So I want the 2nd term in the sequence. That's going to be a sub 2. Is going to be 2 times a sub 2 minus 1. Because remember, n was 2. So this is going to be 2 times a sub 1. Oh, look, that was the previous term. That's going to be 2 times 2 which is 4. Okay? And a sub 3 is going to be 3 times a sub 3 minus 1, which equals 2 times a sub 2. You see where I'm going here, which is 2 times 4, which is 8. Right? And I think we can see that our next term is going to be 2 times 8, which is 16. So a sub 4 is going to be 2 times 8. That was the previous term, which equals 16, and so on. And the last terms are going to be a sub 5 is 32, and a sub 6, oh, ran out of room. A sub 6 is going to be 64. Okay, so we saw the pattern there at the end. But recursive just means the nth term is dependent on the previous term. Okay, let's move on. What if we took the limits of infinite sequences? So for instance, if I wanted to look at as n got really big, the limit as n approaches infinity, and we wanted to know what happens to the sequence kind of way down the number line, to the right, in the positive direction. So given this first one is when sequences converge. Given a sequence a sub n, it is said to converge if the limit as n approaches infinity is some finite number L, okay? And that limit as n approaches infinity will often be written like this. The limit as n approaches infinity of a sub n, okay? That's kind of the notation here, and that's a very bad n, as n approaches infinity of a sub n. Okay, so hopefully you remember that from way back in functions. Let's consider this this sequence right here: 1/2, 1/4, 1/9. We can see that the next term is probably going to be 1/16, 1 over 32, 1 over 64, and so on. And we want to know if it converges or not. Well, converges means it gets really, really close to, and actually will hit that number, L, we'll say. Okay, so in this example, my rule, a sub n, they didn't give it to us, but we can see is 1 over n squared. And this should actually be 1 over 1 here to begin with. But anyway, so a sub n equals 1 over n squared. And if we chose numbers really big for n, so if we took the limit as n approached infinity of 1 over n squared, we are going to approach 0, because like for instance, if I put in n equals 100, I'll get 1 divided by 100 squared. That's going to be a really small number, so that's going to get close to 0. So we'd say that this sequence converges to 0. That would be our number L from the rule. If it diverges, it means that limit as n approaches infinity is infinite or doesn't exist. So the numbers either keep growing or keep getting more negative, or keep getting smaller, or excuse me, growing or more negative. Or that limit doesn't exist. So we'll look at two different examples. This is the first one here, where here's my rule, n plus a half, and notice if I put in n equals 100, I get 100.5. If I put in n equals 1,000,000, I'll get 1,000,000.5. That limit as n approaches infinity of n plus 1/2 is going to keep growing to infinity. As n approaches infinity, the limit will approach infinity. Okay. We can think about this graphically too. Let's very quickly look at some graphs here. Limit of infinite sequences graphically. Consider that first function there. If we were to plot those points where my x values were whatever n was, so, whoa, back up here. So if this was a sub 1, a sub 2, and then I plotted the point 1, comma 1/2 right here. Or 1 comma 1, and then 1 comma 1/2, or 2 comma 1/2. Alright, that'd be my next point. We can see that these points approach 0, just like we suspected when we did that analysis in the previous slide. We could also graph, if we graph the function 1 over x squared, alright, we could see that that function will graph over these dots. So that's the next slide here. I'll take away the handwriting. And there you can see the function graphs right over those dots, f1 over x squared. Okay. Last one, if we looked at that one that was going to infinity, we look at that graphically, you can see that these dots just continue to go on forever to infinity. All right. And one more, if we look at the limit that doesn't exist, so consider a sub n equals -2 to the n. Notice that a sub 1 is equal to -2 to the 1, which is -2. A sub 2 equals negative 2 squared, which is a positive 4. A sub 3 equals negative 3 cubed, which is negative 9, and so on. So this is going negative, positive, negative, positive, negative, positive. So this is not going to approach anything, I don't think. Once again, we can look at it graphically, and when we put it in our graph, instead of n up here, we could put negative 2 to the x and see what happens. But let's look at just the points first. Okay, and we can see that when n is 1, we're here, n is 2 here, 3 here, 4 here, 5 here, 6 here, and so on. We're going to continue to go up and kind of further and further away from the x-axis. So there's no limit. It doesn't go to infinity because they're just getting farther apart, and it doesn't, and that's why it doesn't exist. It doesn't go to infinity. Doesn't go to a value, so the limit doesn't exist. Alright, and that's it for the first lesson on sequences.